Let's see. Welcome, Daniel. We're so glad you made it. Fantastic. Okay.
Can you hear you?
I assume everyone else can hear me.
Can you hear us, Daniel?
Well, he won't hear you through the microphone.
Okay.
There, through this. Okay, you are not muted, which you need to be not muted. Perfect. Okay.
Good evening, everybody. Welcome to the Santa Barbara Astronomical Unit's first Friday meeting for April. It's quite a crowd here tonight. I'm wondering exactly what we put in the advertisement that we're going to show. But we have a few details to take care of before we get to our speaker. It won't take long. But the first thing I want to do is make a presentation to Colin Taylor, our longtime treasurer, for his duty above and beyond the call of duty, interfacing with the museum, getting all the different records straight, producing a fantastic spreadsheet of our money, and skating over all the tax laws that result from a nonprofit that wants to sell things to its audience. But we don't sell at a profit. If it comes to that, read it. Well, I can't get the cellophane off. Colin, I know you're. I saw you walk in. You want me to come up here? Yes. Thank you for the work you do. Okay. The thing says from 2018 to 2022, but it's 2023, and you're still our treasurer. Yes. So I guess we'll have another one next time. Well, thank you.
The trip to Tahiti was pretty nice too.
Yeah. Okay. And now we'll hear an advertisement from our merch manager. Don't run the other way, you'll trip over these cables.
Thank you, Jerry. Hello, everyone. My name is Pat McPartland, and I am the. Thank you. That's my question. I'm the club's merchandise manager. I sell branded club items like mugs and patches and coats and blankets and T-shirts and sweatshirts and that sort of thing. And hats. The prices and examples are on the website. I don't ship, but I will meet you someplace in Santa Barbara if you are interested. And tonight I have a special, I have 3 blankets left that have our club logo on them. And they usually go for $30, but I'm going to sell them tonight for $20. So the first 3 people who want a $20 club branded blanket, let me know. I'll be in the back. And oh, somebody, there's Bruce. All right. And anyway, send me an email if you're interested in anything you see on the website merch page. Back to you.
Thank you. Thank you. And now our third order of the minute is outreach, with our outreach director, Chuck McPartland.
Thank you, Jerry. I guess I got promoted from coordinator to director here. Okay, things are heating up. There's some pent-up demand after the pandemic here. So tomorrow night, second Saturday of every month, we have our star party right here with telescopes set up to look at cool stuff. It's free, so don't hesitate on account of cost. And then we're starting up again at the Bacara. So on Sunday, on Easter Sunday, we'll be at the Bacara starting at 8 p.m. with telescopes set up. On the 13th, Thursday, we have Vieja Valley School for their science night. They call it a science night, but they're ending at 7:30, so it won't be dark, but we can talk to them about astronomy. And then Franklin School, same thing. They're having a science night that ends at 7:30, but we'll do the same thing there. And then third Friday of every month is Westmont Public Telescope Night. They have a nice big 24-inch reflector there in a dome. You can get the whole astronomy experience. Yes, question? Okay, is there a separate spot on the website? On the website, there should be a tab at the top that says Events Calendar, and you can go there. If for some reason you're having trouble with our webpage, you can go to the Night Sky Network page. It's nightsky.jpl.nasa.gov, and you can enter your zip code wherever you are in the US, and it will tell you astronomy events near you, and we register our events with them also. And if you've got some of the apps like Sky Safari, they will go scrounge that data, and they will actually tell you where we are and where we're going to be. Although on the Night Sky Network, some of the school events won't be on there just because they're not really public events. Okay, and then on the 4th Tuesday of every month, it's Telescope Tuesday out at the Big Box at Community Rail Marketplace, where we set up in their plaza, a lot of lights. So we try to synchronize with the most first quarter moons during the year. So that's primarily looking at the moon. But our big event this month, and our kind of a big event for the year, is Saturday the 29th is International Astronomy Day. So we're going to be out at Community Rail Marketplace in the plaza there by the theaters from 10 a.m. to 10 p.m. With safely filtered solar telescopes during the day and various activities. Chrissy's got some heavy-duty grad students coming up from Caltech to do some of the activities, and we'll have some giveaways and things like that. And then we'll break at about 4 p.m. and have dinner, and then from 7 to 10 we'll have another star party there. So that's our events for April. Thank you.
Thank you, Chuck. Now, the banner at the top of our webpage it looks like a thin, dark line, but if you look closely, there's words in it. It doesn't stand out real well. I had to look for it once too, but it is there, and that's the best way to get to our outreach schedule. If you go to our website, remember it's SBAU.org, not .com, but .org. And with that, I'm going to introduce the Vice President. And he will introduce the speaker. Yes, he blundered in.
Come on. All right, we'll get up.
Thank you, Mr. President.
Have we ever seen this big a crowd before, Jerry? I saw nothing but promotion. The museum sent out stuff, and it was in News Press that you give me your copies of. My name's Ron Heron, and I used to be on the radio, and I used to interview these same guys years ago every other Monday morning. And I'd like to know how many of you are new, never been here before, just saw this stuff. Raise your hand. All right, this is a good group, even though we're old. We're looking for some young people to take over for us. I've never known a nicer group of people in my life, and they're all pros and they're all brains. I call them the Brain Trust. I'm the guy kind of like the kid in the morning show on Saturdays and say, "Gosh, Mr. Wizard, what happens if you pour that in this beaker?" That's me. And in fact, I hosted a Monday morning podcast we do. If you go on YouTube, what do they put in? Just SBAU Astro Hour? I assume that would be all you'd need, or look it up and there's a way you can get it. You have to, yeah, it's on YouTube, but we've got 3 years behind us. So much to talk about. I've got my official cup to give to our speaker tonight, assuming he's good. Canada, what if I'm looking at him here? Is that the him in the upper left? Oh, he's good looking.
Good here.
Damn it. Well, we'll introduce him in a minute. I just wanted to say a couple of things. That it is my job as vice president, not only to run the elections in December, but to scare up these first Friday of the month speakers. The last 3 months, actually 4, because we opened again and started coming back after the pandemic in December. And we had a combined visual event with people, maybe a third this number that was back with us. And Jerry was sick, our president, so he did his at home on the screen. And this is the second time we've had a virtual Zoom speaking engagement. So it's going to be interesting, especially from Toronto, Canada, in just minutes. But I had nothing but easy times booking people because I got people telling me who to go after. In fact, a couple of our newest members from Ojai drove over tonight, Rex and Susie. Raise your hand, the Meaches. Rex and Susie Meach. They grew up with the father of our speaker. In fact, he and this gentleman named David Gilman went to Nordoff High in Ojai, and he's driving over from Ojai to join us. I think it's the only Ojai members we have. And then Chrissy turned me on to our outgoing astronomy, Kadam, Raphael, Sigourney, no, that's Weaver. Okay, well, anyway, he's part of the group, I guess, or he's leaving, but he did a great live report, and tonight's the first one back online. So I'm going to introduce him now, and I just urge you to get in touch with me if you have a suggestion, because, ladies and gentlemen, I'm getting no response for the summer. I've sent out 4 sets of emails. I give them about 5 days to get back. Nothing. Like they're all going to get on their yachts and they're going to fly around the world. But okay, well, whatever. So will Pat, and the McPartlands are doing a great job as our secretaries, as well as running merchandise and, of course, outreach. Let's meet this man. I've been talking to him enough, and apparently he's got some accolades going for him already. Not just that he picked up his PhD in physics in 2020, almost 3 years ago at UCLA, but his dissertation is going to be the talk he's giving to us tonight. Strong gravitational lensing as a probe of dark energy and dark matter. Something I know many of you have been losing sleep over. You're going to find out tonight. Dr. Dan is he got an honorable mention nationwide in the CGS ProQuest Distinguished Dissertation Award. They apparently give awards out for these guys that do a dissertation or a thesis. I think it's dissertation when it's for a PhD in physical sciences. He won that award, and they were filed in the years 2019 to 2020. I'm not sure if he won all 3 years or one. He'll tell us. After grad school, Dr. Dan was a postdoctoral researcher at the University of Toronto, where he is now, and where he's coming in to us via Zoom. From 2020 till late 2022, as of January of this year, he holds the Smith AI in Science Fellowship at his university up there in Canada. I want him to also tell us what time it is there, because I have no idea. It's almost 11, my God. Thank you for getting through. This summer, he's going to begin as a Brinson Prize Fellow in Observational Cosmology at the University of Chicago. So we're getting him back. Rex and Susie, thank you. And if his parents are watching us online, David and Mrs. Gilman, this is the young man that's on his way to stardom. Ladies and gentlemen, a big hand for Dr. Daniel Gilman.
And we're just going to take a quick second to get switched over to our Zoom view. Thanks for your patience, everyone. Let's see. And if someone wouldn't mind, let's see, getting the lights, that would be great. Dr. Gilman, how would you prefer to handle questions this evening? Would you like to do questions as we go? Would you like me to put them in the chat? Would you like to do questions at the end? What is your preferred method?
If people write them in the chat, I might not see it. So, but there are a couple stopping points that I can just pause, and anyone who has a question can at that point either write it in the chat or just ask it. I don't know what the easiest way.
Give you the full view here. You've sold out our whole auditorium here. There
Wow.
we go. I just turned the camera around so Dr. Gilman gets a feel for our super full crowd, like he's in the room with us. Oh, yeah, hey, okay. And I'll just be here monitoring the Zoom chat. All our Zoomers, feel free to type your questions into the chat, and I'll make sure they get up to what we're doing here. But also, people on Zoom, please do keep yourselves muted for the whole thing, because we hear you on the speakers in the auditorium if you're talking. Okay, sorry. Thank you. Go ahead, Dr. Gilman. I am now muting me.
Okay, yeah, so if I share my screen, everyone can see it, I suppose. Let me try. Can you guys see my screen? Can people hear me? And can you see my screen? Was that a yes from the people in the auditorium as well? I see the people on Zoom are good. What about the people in the auditorium? Yes? Okay, great. I saw someone put a thumbs up in the back. All right, cool. Well, yeah, thanks a lot for the introduction. Yeah, it's great to be able to talk about science, and it's a privilege to be able to do it, really. You know, so as Ron said, I'm going to talk about dark matter and dark energy. I mean, there are many ways that people study these things in cosmology. The one that's closest to my expertise is strong lensing, so I'm going to focus on strong lensing. And you know, I really hope that you guys haven't lost too much sleep over this, but if you have, hopefully after this talk, you know, as Ron alluded to, you'll sleep a little easier with some more knowledge. Okay. So let me go ahead and get started. So I like to kind of start these talks about dark matter and dark energy with this kind of amazing experiment that was done, I guess now over 20 years ago. So first, you know, imagine if you put a tennis ball about 100 meters away, or in American units, I guess that's 1 football field away, and imagine how big it is. Okay, so this is about 1/25 of a degree on the sky. And in the mid-90s, the Hubble Space Telescope was pointed at an area of the sky that was about that big in angle. And it just stared at it for a while. And it produced an image that is now called the Hubble Deep Field, or the Hubble Ultra Deep Field. I think there's actually a deep field and a Hubble Ultra Deep Field. And if you look at this, okay, you see this. Okay, so this is, again, 1/25 of a degree across. It was on a completely, you know, to our eyes, black patch of sky. And if you look at it very closely with a space telescope, you see all of this structure, right? And all of these things are actually galaxies. Let me hide my view here. So all of these things are actually galaxies, right? So these, and each one of these galaxies contains billions of stars and probably also billions of planets, right? And so this, when this came out, it's very humbling, right? It's still very humbling. It didn't have a big effect on me at the time because I was like 4 or 5 years old, but I mean, as I got older, I started to appreciate what this meant. But then you get humbled again when you realize that all of this is still just 5% of what we know exists in the universe. And the other 95% is something fundamentally mysterious to us. And there's these 2 additional components that the universe is made of, in addition to atoms and you know, what scientists call baryonic matter, which is basically everything in our own existence. Okay, and so the first additional component that we know exists is dark matter. Okay, so this is about 5 times as abundant as regular matter. And what dark matter is some particle that only appears to interact gravitationally with regular particles. So none of the forces that are relevant for our everyday lives seem to interact with dark matter. And so for that reason, it is you know, flying through you as we speak and just not interacting with any of the atoms in your body. And if we return back to the Hubble Deep Field, okay, and we imagine with very sophisticated simulations what this would look like if we could somehow see the dark matter, you would have an image that looks something like this. Okay, so you see this blue now is the mass in dark matter, and you see all of this structure, right? There are these filaments. It's kind of like a cosmic web, and at the intersection of the filaments, there are these big blobs of big, roughly spherical blobs of dark matter, right? And if we zoom into one of these blobs, in our current understanding of galaxy formation, we should find a galaxy. And the technical term for these gigantic blobs of dark matter are halos. And in order for us to make sense of the universe, galaxies need to reside inside of these gigantic halos of dark matter. It's actually very difficult to explain how galaxies even exist without dark matter halos. And to put this in a slightly more quantitative picture, okay, so this is an image, or sorry, a graph of the halo mass function. It's basically telling you how many halos there are as a function of how massive they are, right? So not only does the existence of dark matter predict halos, our best theory, which is this cold dark matter, which I'll return to in a second, what that means. Okay, our best theory tells us that these halos exist, and it also tells us how many there are, right? So as you move left and right on the x-axis, this is essentially the mass. So in logarithm, the log 10 of the mass. So a 10 means it's 10 to the power of 10 solar masses. And on the y-axis going up and down, this is how many of these halos there are. So on the far right, there are galaxy clusters, which are essentially the most massive gravitationally bound objects in the universe. As you start going to the left, you start finding some of the most massive isolated galaxies. Our galaxy, the Milky Way, lives inside of a dark matter halo that is something around 10 to the power of 12 solar masses. So this is 1,000 billion times the mass of the sun. Okay, and then once you get down to 10 to the 10 solar masses, these are small satellite galaxies that orbit around the Milky Way. And then once we get about a factor of 1,000 times smaller, we start finding the smallest known galaxies, which again are orbiting our own galaxy. And this line that goes through all of this is the prediction. So that is how many halos we think should exist. Okay, and as I will talk about later in my talk, okay, there is some threshold here where we don't expect galaxies to have halos anymore. So if we go back to the previous slide, so this really massive halo had a galaxy in it, but once you get below a certain threshold, all right, the halos do not retain their stars very efficiently, and so they shouldn't have galaxies in them. And so these halos are, what I'll refer to as the dark halos or the darkest halos. And these things, they should be out there. And one of the things I'm going to be talking about a little later is how we try and detect them and why we care about their existence in the first place. All right, so that's a little bit about dark matter. So the rest, okay, the green, this makes up about 70% of the rest of the universe. Okay, and this is something that in some ways is even more fundamentally mysterious than dark matter, and that's dark energy. And the way to think about dark energy, or at least the way I think about dark energy, is in terms of what it does to space and the universe. And so in order to illustrate this, I attempted to animate these slides a little bit. So we'll pretend like we're living inside of one of these galaxies, so the one in the middle. And I want to introduce this concept of a cosmic ruler. All right, so this is something that is keeping track of distances in cosmology. So this is not the distance between like your hand and your face. This is the distance between two galaxies. So these are cosmological distances. And the next thing I'm going to do is lay down a grid. Okay, so this grid is basically going to expand and contract in proportion to our cosmic ruler. And we'll suppose that this is an image taken billions of years ago, which of course this light has traveled billions of years to reach us. So this is essentially an image of the universe billions of years ago. And then I'll turn on the clock and let time go forward. And as you allow time to advance, right, we will see space expanding until we get to the present day. Right? And notice that we are here in the center, and everything appears to be expanding relative to our position. So things that are far away are moving away from us, and things that are further away are moving away from us even faster. And what's interesting is that if you were to keep advancing time, you would see even faster expansion than the expansion that happened from the past until today. Right? And so this accelerated expansion of space is essentially what's attributed to the existence of dark energy. Or a different way of putting this is that we're pretty sure something like dark energy exists, at least in part because of the accelerated expansion of the universe. And as I will talk about later in the talk in more detail, because the types of measurements that we make and to learn about dark energy have to do with expansion, cosmological distances, or the distance from us to distant objects in the universe, are very closely tied to our understanding of dark energy through the expansion of space. Okay, so that's it. That's what our universe is made of. There's 5% regular matter, about 27% dark matter, and then the rest is dark energy. Together, these three components comprise our cosmological model. So this is usually abbreviated lambda CDM. I'm going to, from now on, refer to it as lambda CDM. It's called lambda CDM because CDM is an acronym that stands for cold dark matter, and dark energy is usually abbreviated with the capital Greek letter lambda, okay? And lambda CDM is actually remarkably successful. It explains basically every observational test we throw at it, it passes, and it explains or it predicts our measurements. And I'm not going to go through this list. I just made this list so that you guys would believe me, and when I say that lambda CDM is actually a really good theory. And the kind of issue with this, there's two big issues with lambda CDM being a good theory, is one, that we have no idea what dark energy is, and second, that we have no idea what the particle nature of dark matter is. So, I mean, from the point of view of a physicist, it's actually quite annoying, right? That you have this theory that seems to explain all of your experiments that you do in space, and yet the two dominant components of your theory, you have no idea what they are, and you have really no description of them from a first principles physical point of view. So, to remedy this situation, our job as physicists is basically to come down and try and break the theory. So even though it explains all of the measurements we've done to date very well, we could consider making even more stringent tests of the theory, and eventually it will break down, or it will reveal some gap in our understanding. And you know, when you break the theory, when you reveal something that it doesn't adequately predict, this could lead you to discover new physics. And hopefully, eventually, we will discover new physics that points us towards the nature of dark matter and the nature of dark energy. So, as I said, there are many ways that you can do this. The one that I'm most familiar with and most passionate about is strong gravitational lensing. And so that's what I'm going to focus on for the rest of the talk. And to introduce lensing, I like to start with this movie. This was made by Yashar Hetsabe, who's also in Canada, as a matter of fact, at the University of Montreal now. And as I play this movie, what you should do is focus on the fish, okay? As the fish approaches the corner of the fish tank, you will now see two images of the fish, right? And so this is happening because the light leaves the fish and then it's deflected by the glass in the corner of the fish tank. So you see the fish twice. And this is somewhat analogous to what actually happens in cosmology. So if you have some very, very massive object, like a galaxy and its dark matter, and it's in front of some source that's bright, some true source of light, the light from that source is deflected by the gravity associated with this massive object. And so you will observe the source at a position that's displaced from its true location. And if you have very precise alignment with the source, you will actually, or you can actually see the source become multiply imaged. So all this requires is a very, very massive thing like a galaxy and all the dark matter around it, and then some very bright thing directly behind it in such a way that the light from the source becomes distorted and warped around the foreground galaxy, and you see the source multiple times. So this is strong lensing. And in order to kind of make sense of some of the pictures I'm going to show you, I want to explain what the source is. So first of all, it's usually a quasar inside of a galaxy. So a quasar is a black hole that is accreting material. As the material circles the black hole, it gets very hot and it shines very brightly, right? And these things are in the center of galaxies. So this is now an actual image of one. So you see the galaxy here. This is a big, beautiful spiral galaxy. And in the middle, this bright thing is a quasar, right? So this is the source, usually. And the kinds of lenses I'm going to be focusing on here are galaxies and their dark matter halos. So we'll put now the lens in front of the source. And you can now shine light from the source. Some of the rays will be deflected around this massive galaxy and its dark matter halo, and then they will arrive at our telescopes. And so from our vantage point, we will see the source multiple times, and any kind of extended image of the source we see is going to be highly warped and distorted. And so this is kind of a side view. Okay, I'm going to show a front on view soon. So right now, so this is what it looks like from the front. This is what we see. This is actually a Hubble Space Telescope image of a strong gravitational lens. What you're looking at here, this blob in the middle is a galaxy. It's just kind of a regular elliptical galaxy. The 4 bright points, these are the multiple images of the background quasar. In this case, there are 4 images of the same quasar. And then this ring is the galaxy that surrounds the quasar that's being warped around the foreground deflector. So, I mean, these things, again, this is an image from the Space Telescope. If you had exquisite vision, you could imagine looking up at the night sky and seeing this with your own eyes. This is a very in-your-face example of general relativity happening, or the deflection of light by gravity. And that's not the only one we know about. There's actually order 10, I forgot exactly how many there are, maybe 30 known quadruply imaged quasars. So here's 6 examples. You can see they're all pretty spectacular, right? So, and they have different morphologies, right? Some of them you only see the quasar images. Other ones, there's a prominent ring. Some of these, like the one in the bottom center, DESJ0408, this actually has multiple rings. I'll come back to that one a little bit later in the talk. But the point is that these things are fascinating, and they're actually very useful for us. They're not just fascinating to look at, they also have a lot of utility for doing cosmology. So I want to talk a little bit before I go into details about just kind of a schematic overview of how we use these things. So first, because lensing is a geometric effect, or at least part of it is a geometric effect, the lenses that we observe, they contain information about distances. And because these things are so far away, these are cosmological distances that depend on the expansion rate of the universe. And so the first thing that these strong lenses can do for us is allow us to measure cosmological distances. And that is going to have implications for measurements of dark energy and the expansion rate of the universe. So the other thing that I will come to later in my talk is that as this light travels to us, it's passing through lines of sight that should be populated by many, many dark matter halos. And so every time we look at an image of the lens, we are, at least in principle, looking at something that contains a tremendous amount of information about all of the dark matter structure between us and the source. And cold dark matter, as I mentioned previously, it makes very precise predictions for how many of these halos should exist. And in particular, cold dark matter, this particular variety of dark matter that is sort of the standard hypothesis for what dark matter can be, it predicts that there should be lots and lots of low mass halos between us and the source. And so this is a prediction that we can go out and test with lensing. And so I mean, after that kind of overview that was kind of motivating the rest of the talk, I'm going to break it up into 2 parts. So the first is dealing with measurements of cosmological distances and what they tell us about dark energy. And this, it gives me an opportunity to talk about the Hubble tension, which is something that many people are talking about right now in cosmology. And the second topic that I'm going to talk about afterwards is how we use strong lenses to look for very low mass, completely dark halos that we know must exist if cold dark matter is correct. So I think this is kind of a natural stopping point to take a question, if anyone has questions. If no one has questions, I'll just continue talking. What do people think?
Okay, I've unmuted us here in the auditorium. I'll relay the question if you can't hear it. What's the question?
In the 6 images of multiple images of things that have been lensed, there were often 3 close together and then 1 separately, and I wonder if there's a reason for that or if it's Can you bring that slide down?
So I'm not sure if you heard the question, Dr. Gilman. The question was, in that earlier slide with the 6 images showing the lensing, yes. The distribution seemed to be 3 close together and 1 that seemed further away than the other 3. Is there a correlation? Is that a pattern?
Right. So where the images appear and how close they are to each other and stuff, this depends on both the shape of the deflector, so that the shape of the galaxy, if it's more elliptical, you might have a different configuration of the images. And then it also depends on the position of the source relative to the lens. So if you have, a nearly circular lens and the source is immediately behind it, you will see something like the bottom left, where the images are kind of symmetrically distributed around the deflector. But then if you have something that's very elliptical, or the source is offset from the center, then you can get something like the top left, where you have kind of 3 images close together and then 1 counter image.
Yeah, we've got another question.
Is there such thing as hot dark matter?
Is there such a thing as hot dark matter is the question.
Is it subject to temperature?
Does cold really mean temperature? Is that the reason we say cold dark?
Right, yeah, so that's a good question. So in this context, cold is sort of a proxy for how quickly the dark matter particles are moving in the early universe. And so cold particles are moving slowly or non-relativistically in the early universe. And there is actually such a thing as hot dark matter. It turns out that it's ruled out by the existence of galaxies. So if you have dark matter where the particles are moving too quickly at early times, you actually can't form dark matter halos, and then we wouldn't have galaxies. Or if we had galaxies, they would look very different from the ones that we see in telescopes. So yeah, it's a good question. In principle, hot dark matter could exist, but we know that that's not the right theory.
Excellent, thank you. Any other questions from the audience here in person? Yes. I'm sorry, what? I really tried to get rid of the feedback. It's not feedback per se, but highway. After I do close the speaker's voice, I tried. I messed with the EQ. The short answer is no. Sorry. Was there another question? Oh, so the question is about the lens. Could you tell us more about that term? Is it how we're perceiving it? Is it an actual physical thing? Can you tell us more what you mean when you are talking about a gravitational lens?
So yeah, I guess usually people say a gravitational lens system, and there you just, the system refers to the source, which is usually a galaxy and a quasar. And then the lens itself is a galaxy, and the gravity from the galaxy produces a lensing effect, or an optical distortion of the light from the background source. And so when I say like the lens, what I mean is, when I say the lens, usually I'm talking about the galaxy that's doing the lensing. And when I'm talking about the whole thing, I might say the lens system. I don't know if that answers your question.
Yes, that answered the question. Great. Other questions from the crowd here? Okay, I think we're ready to head on back.
All right, cool. All right, so part 1. So strong lensing, distances, and dark energy in the Hubble tension. So this actually goes back to 1966. So the idea that you could use lenses for this purpose. And Sir Refsdal is the one that sort of first proposed this. He wrote it in the abstract, he wrote this paper about it, and then spawned what is now the field of, or subfield in cosmology, which is time delay cosmography. So time delay, the reason why it's called time delay will become evident very soon. Cosmography refers to just the measurements of distances in cosmology. So time delay cosmography refers to the measurements of distances with the time delays between images in quadruply imaged quasars. So as it turns out, each one of these images arrives in our telescopes delayed relative to the other images by some amount. Because there are 4 images, there are 3 time delays. So you'll pick one of them, so say image A, and then you'll measure the relative arrival time between image A and image B, then the relative arrival time between image A and image C, and then the relative time between A and D, okay? So the data are these 3 time delays. And to measure them, what I should say here before I talk about how you measure them, I know that this is an equation, and it's actually the only equation that's going to appear in my talk. So please don't leave. If you're in the auditorium and you see just stay, it will go away soon, I promise. So basically what this equation is doing is it's relating the time that it takes light to reach us to things that depend on the cosmological distance, which is this d delta t. That's something that we want to know. And then there's something that depends on the geometry of the lensing. So basically the positions of the images relative to each other. And then the last term, this is the technical term is the gravitational potential of the galaxy. This is something that depends on the lens itself, or the galaxy that is doing the deflecting of the light. And if we want to use this equation and lenses to measure distances and learn about dark energy, there's two things we need. Right? So first, we need to measure the relative arrival time between lensed images. And the second thing we need is a model for the deflector, or a model for the galaxy and its dark matter halo that are producing the multiple images and creating the lensing effect. So the first one is really just a pure measurement that you can make. What this is showing is for one particular lens. It's actually the lens that I was just showing. These are the light curves of the 4 images collected over a very long time. I mean, this one is done over a period of years. And what's shown on the x-axis, if you move left and right, is time, okay? And what's shown on the y-axis, going up and down, this is how bright the image is, right? So here, the quasar, which is being quadruply imaged, is time variable. And because you see these images arriving to you at different times, because the light has taken a different amount of time to reach you, it's taken a different path through the universe, each one of these curves is actually shifted relative to the other ones by some number of days. And the number of days depends a bit on the configuration of the lens. It could be anywhere from 1 day to hundreds of days or years. But you can actually, if you do a lot of monitoring of these lens quasars, you can just collect their light curves, wait for some feature that's going to show up in one image, and then you wait some period of time. That same feature will show up in another image, and then you can read off the time delay from these light curves. So that's how you measure the time delays. The next thing you need is a model for the lens. And this is actually really complicated because it involves simultaneously inferring the mass that's doing the lensing together with what the source looks like by reconstructing the lensed image. So it's a very computationally intensive process. It requires a lot of code. My collaborator made a movie that I like to show. Whoops, started kind of prematurely. For me, it does a very good job of illustrating what's happening when you do lens modeling. So basically on the left, the top left shows an input image. So you can think this is like, this is what you see in the telescope. Okay, the bottom left shows the true source that produced that lensed image. So the bottom left is the true source. The top left is the lensed image of that source. And then in the middle, it's going to show, after you have fiddled around with the mass of the galaxy, the best model for the light that you see, and then the best model for the source. Okay. And this number n max that appears in the center bottom panel is basically a proxy for how complicated the source is. So when n max is 0, the source is just a circle. And as n max increases, as I play the movie, the source will become more complicated, and you'll see that the reconstructed lensed image and then the underlying mass distribution that produced that image is getting better and better. All right, so I'm going to go ahead and play the movie. So you see already by n max equals 4 that the reconstructed image starts to look pretty good. Once you get to n max equals 10, you start resolving the spiral arms, and then these kind of spiral features show up in the lensed image. And then eventually you get to such a detailed model for the source that your data can't really improve the lens anymore. So this is lens modeling, and it turns out that people are actually really, really good now at doing lens modeling. And my favorite way to demonstrate this is using this amazing system, which I'm going to describe now in the next few slides. So what you're looking at here, this is actually a zoomed in image of a galaxy cluster. And what you're seeing, this kind of spider looking thing in the back, that's just a regular spiral galaxy that is behind the cluster. And because it's behind the cluster of galaxies, it's being lensed and it appears magnified and a little bit bigger than it actually is. And so this thing's really far away. it looks big because it's being magnified. So the other thing, this bright kind of blob in the bottom left, that's a regular galaxy that's part of the cluster. So there's a cluster of galaxies. There are other galaxies off screen that you don't see. This is just one that happens to be kind of in front of this spiral galaxy from our vantage point. And the other thing that you'll notice is that one of the spiral arms from this background galaxy is sort of wrapped around this foreground elliptical galaxy in the cluster. And what's happening there is that this spiral arm is being strongly lensed by this foreground galaxy. So the other arms are too far away, but the spiral arm that is kind of behind this elliptical galaxy gets strongly lensed. And that's why it appears in kind of a circle around the foreground galaxy. And what makes this really, really cool is that it just so happened that a supernova detonated in the spiral arm that is being strongly lensed by this foreground elliptical galaxy. And that supernova became quadruply imaged. And those 4 images are labeled S1, S2, S3, and S4. And just in case I guess I didn't say it. So a supernova is the explosive death of a very massive star. So eventually stars will burn all their nuclear fuel. And when that happens, if they're big enough, they will explode. And sometimes these explosions are so huge that they outshine galaxies. So this is one such explosion, and it just happened to be quadruply imaged. Now, this is, I mean, just this image itself is pretty insane, okay? But what makes this even crazier is this paper. So the title is Deja Vu All Over Again, The Reappearance of Supernova Restall. And I took a sentence out of the abstract here, and I put it at the bottom. Almost all lens models of the cluster have predicted that a 5th image of the supernova should reappear within a year. Okay, so looking at this strongly lensed supernova, people had models for the cluster, for its mass distribution, and they predicted in advance that we should see a 5th image appear, okay, of the supernova. And not only did they predict that a 5th image should appear, they predicted when and where it should appear in the cluster. So this is an image of the field taken in 2011. So this is before we saw the supernova. And so you see there's nothing in the circles S1, S2, S3, and S4. And there's nothing in the circle labeled SX, which is the predicted reappearance location of the 5th image. So if we go now to 2015, so this is when the supernova was first seen. You see the 4 images of it. So those are that's the quadruply imaged supernova. And you see there's still no SX. There's no 5th image. And what these lens models predicted, the ones that I referred to with that sentence in the abstract, they predicted that sometime around the end of 2015, I forgot exactly the month, but sometime around the end of the year, you should see the 5th image. And so if we look now, December 2015, you will see now there is a 5th image of the supernova appearing precisely where it was expected to appear. So this is remarkable. I mean, I think that this does a really good job of showing how good people are at lens modeling and also how well we understand this physics of lensing. And that's important because we want to use lensing to understand physics that we don't understand. So we need to make sure we understand lensing very well before we do this. And this, quadruply +1 image supernova, this has led to a measurement of cosmic distances and the Hubble constant, which I'll explain in a second. But unfortunately, it's not published yet, and it's still being peer reviewed, and so I can't say anything more about this. But I can talk about measurements that have been made. So this is another kind of spectacular strong lens system that was analyzed in 2020. And there's a lot going on here. So G1 here is a regular galaxy. That's an elliptical galaxy. You'll see A, B, C, and D. Those are 4 images of a background quasar that's behind G1. G2 is a satellite galaxy of G1, so it's a small companion galaxy, and it just so happens to be splitting image C. So image C is itself being doubly imaged by galaxy G2. There are 2 other galaxies, G3 and G4, that are off screen. G5 is another pretty massive galaxy that's in the background. And what makes this system really, really cool is that there, in addition to the lensed quasar and its host galaxy, there are 2 additional sources that are being lensed. And so they're labeled here S2 and S3. You can see that S2 is lensed into this arc with a counter image to the upper right of B. And then S3 is lensed into this arc to the upper left of image D. So this system was modeled in 2020. So on the left, there's the data I just showed you, and the right is the reconstructed lensed image that you get from reconstructing the lens, mass, and the source. And this is done with the open source lens modeling software called Lenstronomy, which you can go and download. It's open source, so anyone can use it. And once you have the time delays and the lens models, you can now convert this information into distances. And so that's what I'm showing here. This is the joint distribution of two distances. The one on the y-axis, this df delta t, that's actually the one that is we really care about. And the point is that once you have these distances, you can assume a cosmological model. So what we can assume lambda CDM, and we can turn these distances into parameters. And the parameter that is usually used is something called the Hubble constant, which is the expansion rate of the universe today. So we measure these distances, we assume a cosmology, so we'll assume lambda CDM, and we get the expansion rate of the universe today. And this kind of measurement has been done for 6 lenses to date. And since each lens is independent of the others, you can multiply the results or the likelihoods from each one. And you get from these 6 lenses that the expansion rate of the universe today should be around 74. And the units are kilometers per second per megaparsec. Okay, so we get 74 from lenses. There are many other measurements of the expansion rate of the universe today, H naught. Okay, this figure, I think it's a little dated now, but it does a really good job of compiling all of them. So we see here towards the bottom, the yellow points, these are lensing related mass model dependent measurements. You'll see other stuff like gravitational waves are now being used to measure cosmic expansion. We go up towards the top, there's this category called Cepheids type 1a supernova. That's what SN1A stands for. And you see that those measurements are all really precise. Okay, those are actually the most precise measurements we have, and they're all around 73 kilometers per second per megaparsec. And if we go up more, we start getting into stuff with the CMB. CMB stands for cosmic microwave background. I'll explain what that is in a second, but the point is that these measurements don't agree. Right? And this disagreement between measurements of the Hubble constant is what's called the Hubble tension, or what some people are now calling the Hubble crisis, or the crisis in cosmology. Right? And you see that these measurements are grouped into indirect and direct. And to understand why it's a crisis, it's important to understand what is meant by an indirect and a direct measurement. So here is a cosmic timeline. So on the far left, we have the beginning of the universe and the Big Bang. The cosmic microwave background light, this is the oldest light that we can see. It's been traveling to us essentially for almost the entire age of the universe, right? And then much, much later, we have galaxies forming, and then today is April 7th, okay? So this is time. Indirect measurements are ones where you have something like the CMB that is intrinsically something that is probing the universe at very early times. And you use this to measure some distance at very early times, and then assuming a cosmology, you can then propagate that forward into what the expansion rate should be today. And so in that sense, it's an indirect measurement, because the measurement you're actually making is of cosmic expansion at the epoch of the CMB, but then assuming a cosmological model, you can extrapolate that to the present time and predict what the expansion rate should be. Lensing is grouped together with direct measurements because it's happening at such late times. So long after galaxies are forming, you can do lens modeling, measure distances, and turn that into predictions for what the Hubble constant should be. And then the most precise measurements, these type 1A, the ones that come from supernova, these are really the most local measurements that we have of cosmic expansion. So they are basically as close as you can get to a direct measurement of the Hubble constant. And as I said, right, the tension is in the disagreement between these two numbers. And it's interesting that things that are sort of measuring the local expansion rate or the expansion rate at very late times give you something like 73 or 74, whereas measurements that rely on early universe physics extrapolated to the present day give you something like 67. And the disagreement with these numbers is statistically extremely unlikely. It's very unlikely that these are just random chance, that this is just a random fluke of statistics. And so this has people excited because it could be an indication of new physics. So I'm not going to talk too much about this, but I mean, one possible solution for this is something called early dark energy. It's something that's gotten some attention lately. Basically, you change the expansion rate of the universe at early times in such a way that when you extrapolate that to the present day, you predict a larger value of the Hubble constant. The other possibility is that one or more of the measurements are wrong, right? There's actually no tension, we're just wrong. And for this reason, it's important to have many different types of measurements because it becomes very unlikely that everybody is wrong and still getting the same answer even though they're wrong, right? So you want to have many different types of measurements in order to eliminate option 2. And I think it's still too early to say which option I think is true. I have my opinion, but my opinion doesn't really matter. Only the data and the science matters. And so I think in the next 5 years or so, we will know the answer to this question, which is exciting. It could be new physics. All right. So this is also another kind of natural stopping point, but I don't know. Do you think I should just keep going and take questions at the end, or should I proceed to dark matter?
We overwhelmingly vote to keep going.
Okay. All right. We'll keep going. So part 2. So this is now the hunt for the smallest, darkest halos with strongly lensed galaxies and quasars. And I'll just say that this is something that I work on personally, so I'm very excited about part 2 of the talk. So just to get started, I mean, I think it's worth asking, like, why do we care about finding these small dark halos? It sounds very hard. Like, why would anyone put time and effort into doing this? So the first reason is that the number of these low mass halos actually depends on the particle nature of dark matter. And this is revealed through cosmological simulations like the one I'm showing here. On the left, this is cold dark matter. So this is our standard cosmological model of dark matter. And on the right is something called warm dark matter, where you see that these very low mass halos don't exist anymore. And the difference between these two types of dark matter is a little technical. I'm not going to explain it in detail, but basically it has to do with how the dark matter is produced in the early universe. And it has ramifications at much later times, right? Because we basically have a situation where no small halos exist in warm dark matter relative to cold dark matter. And going back a little bit to the galaxy formation, this is going to lead into another reason why we want to use lensing and why we want to detect these low mass halos. So, the largest halo, the big one in the center, is going to have a galaxy in it. Then some of the bigger halos around the central halo, the subhalos, they might have galaxies in them too, but most of these things are completely dark, okay? Most of these halos don't have a galaxy. They're below the threshold of galaxy formation. And the other reason that we want to look for these things with lensing is because lensing is a purely gravitational phenomenon. So we actually don't care whether these things have galaxies in them. It allows us to basically get around that complicated issues associated with how you trace light and mass in galaxies, and it allows us to push lower in mass to regions where these halos just don't have any or enough stars and gas in them to be visible. And, to connect this a little bit back to lensing, right? If you imagine in cold dark matter, you might have a situation on the left where between you and the source, there are lots of these little halos. And on the right, in warm dark matter, you would have just a few, and they would be very big because the only ones that survive in warm dark matter are the more massive halos. And this is actually really challenging to do because this is all we see, right? All we see is light, and we want to somehow infer the presence of these invisible blobs of mass that we know should be on top of the lens and participating in the lensing effect that we observe. And there's basically two ways that people go about doing this. So one is in the lensed arc, because the lensed arc is spatially resolved, which means you can essentially see it clearly. you can detect individual halos if they appear or if they happen to appear on the arc in projection. And the second one, which I'll talk about after method number 1, is that these low mass halos actually change the relative brightness between images in a way that we can measure. So beginning with option 1, this is kind of an extreme example. This is not really dark matter related. This is more galaxy related. So this is a cluster of galaxies that together are producing a lensing effect on some background source, which you see is lensed into this gigantic arc. And if we zoom in to G4 here, this is a satellite galaxy that just so happens to be on top of the arc. And you can see just by eye that the presence of this galaxy is splitting the arc. Okay, so if we didn't see the light from G4, we could infer that there was something very massive there just by seeing the arc kind of warping around empty space. And that's very similar to what people do with this technique called gravitational imaging, which is where you're trying to detect dark matter in the arcs. And to illustrate this, I simulated on my laptop yesterday, actually, what a lens would look like with no dark matter in it. So that's on the left. Okay. And now if I add a really small, and so in cosmology, small is about 100 million times the mass of our sun. So that would be very small for cosmologists. And I put it there where see the black circle on the left. Now, you can't really tell the difference if it's 100 million times the mass of the sun. Okay? If it gets to be 1 billion times the mass of the sun, then you notice a small effect. Okay, if I flip back and forth, if you look carefully, you'll see change in the arc. And by the time you get to 10 billion times the mass of the sun, right, then it's a very noticeable effect. And so this has been done. So this is a paper from 2012. I think, to my knowledge, it was the first real demonstration of this technique. What I'm zooming in on now, this is the data. So you see the strongly lensed galaxy here. This is the model, excuse me. So the model looks pretty good, right? It does a very good job of fitting the data. And if we go down here, this is the inferred mass in dark matter, and you see this overdensity popping out, which turns out to be about a 10 billion solar mass dark matter halo that was detected purely gravitationally because it appeared on top of this lensed arc. So it's remarkable that this works, that people have actually done this and detected these dark matter halos in this way. And kind of returning back to this figure that I showed at the beginning of the talk, this halo that was detected, this was by Simona Vighetti, she's at the Max Planck Institute in Munich, is about 10 billion times the mass of the sun, which is 100 times less massive than our galaxy's dark matter halo. So it's cosmologically speaking, it's very small. But it's still about 1,000 times more massive than this population of completely dark halos that are below the threshold of galaxy formation. And detecting these dark halos is really what we want to do if we want to discriminate between different models of dark matter and test cold dark matter. So this is where option 2 comes in, which is where you look at the relative brightness among lensed images. And I made kind of the same demonstration now, but just looking at the images of a quasar that's being lensed. And so here I'm showing with no halo how bright that image is. So this is the image that's being pointed at with the arrow. That's the image I'm talking about. And I guess I should have said this before, but on the right, this is just a map of where the dark matter is. So I didn't put any dark matter halos into this particular simulation. So you see nothing on the right, but now I'll add a 100 million solar mass blob of dark matter. You see it appearing there faintly on the right. And already, right, this image goes from having a magnification or a brightness of 8 to a magnification of 18. Right? So it nearly doubled in brightness from the presence of this 100 million solar mass dark matter halo. And if we get to 1 billion solar masses, then it's about over 3 times as bright as it would be with no halo there. And so this is, very powerful technique to detect lower mass halos. It's also very expensive because there are so many halos. You have to run these very expensive simulations of them. And so what I'm showing here is this particular lens RxJ0911. And on the bottom right, this is a simulation that I or one of my collaborators would run to analyze this system. And what this schematic is supposed to demonstrate is that you have these 4 paths taken by the light. So they originate on the far left here at redshift around 2.77, and they terminate on the right. That's essentially where the Earth is in this schematic. And you can see that each light ray is taking a different path through a line of sight that's populated by many, many of these low mass halos. And this demonstration that I made here, this was just with one halo. But with these kinds of simulations, we can do we can predict the effect of many halos and what effect they would have on the data, which is much more complicated than the effect of just one single halo near an image. And what you get out of this type of simulation is actually plausible maps of the dark matter halos in lenses. So this is that's what's shown on the right here. I'm going to zoom in now and talk about this in a little more detail. So this top row, this is for a particular lens B1422. And what's shown in the panels are 2 possible configurations of dark matter halos in this lens. And when I say that they're possible, what I mean is that they give you a lens with the same image positions and the same relative brightness among the images. And so again, these possible distributions of dark matter are just produced from the simulation. We run many of them, millions of them per lens. And then we go in and we check, okay, did any of these actually produce a lens that looked like the one we observed? And if they did, then we save them and we analyze them in more detail. And it was done for 8 lenses. So I'm showing now 4 of them. Well, the next few slides, I'll show 2 more in addition to the 2 I already showed. And you can see that, there's some interesting diversity in the kinds of dark matter that is allowed by the data, right? So, for this particular lens, you can see that you could have lots of structure, and in some cases, just a few halos in warm dark matter is allowing you to fit the data. But generally, these lenses seem to require substructure. And so you see the kinds of dark matter models that are fitting the data, they tend to have lots of halos around. And I should say, right, that here the red is basically the mass in dark matter. So if you see lots of red, it means there's lots of dark matter halos around. So from this type of analysis, and then before I go on, I'll just say, if you're interested in this work, Vice did this really cool review of it. I linked to this article on my University of Toronto website, or you can also Google the title. I think this article did a really good job of explaining kind of the motivation and then the results of this type of analysis. And so if you now use the relative brightness among lensed images, you can improve by over a factor of 100 in mass over gravitational imaging. So this green line now is the constraints or the measurements that came out of this analysis that I was showing you in the previous slides. And you can see that now we're certainly below 10 to the 8 solar masses. So this is 100 billion times the mass of the sun. And we're almost now pushing into this regime where the halos, should they be orbiting our galaxy, would be completely dark. And so we're almost there when we're almost detecting these dark matter halos that lie below the threshold of galaxy formation, that are sort of like the holy grail of dark matter physics or dark matter astrophysics, because they can tell us so much about the nature of dark matter. And it's also just kind of a remarkable prediction, right? That cold dark matter tells you that there should be these 1 million solar mass blobs of dark matter floating around the universe, right? If you can actually detect these objects, it's a pretty remarkable confirmation of cold dark matter and a validation of it as a theory. Okay, I can't talk about astrophysics without mentioning JWST, and so I'll just briefly say that in the future, right, and by the future I mean like the next 2 years, we should have at least 20 or 30 more lenses than we currently have, and this is made possible by a JWST program that my collaborator Anna Nierenberg was awarded. And so some of this data is already arriving. I'm not going to go into technical details about why JWST is so good for this type of science, but I'll just say that we think that with the additional lenses that we get from JWST and then the improved quality of the data, we'll be able to detect, hopefully, these really dark halos that we're after. And right, so that's actually all that I have. So thanks for your attention.
There you go.
Are they gonna do it again or not?
Dr. Gilman, can you hear me?
I can, yeah.
Do you have to leave the lens open for a long time, like for a deep field, to be able to see the lenses? Instantly, the minute you lock in on the damn thing, you see it. I think I've asked this of my guys that all have telescopes. Is it instant or does it take a while?
It's not instant. No, it requires a certain number of orbits in order to get a deep enough image of the lenses with Hubble. I'm not sure how long the exposures are with JWST. I mean, it's not that, so they are very bright, right? I mean, quasars are bright on their own. And if you have a lensed quasar, it's being magnified, so it's even brighter. So it's not super difficult to measure the quasar brightness, but then to get the deflector, the lens galaxy, then it requires a little more time.
Well, we got questions. Go ahead, sir. I'll pass it on to him.
So,
See you next month, hopefully.
is this
First prize.
research that we're almost on the edge of? Is that going to tell us like what the dark matter is?
He's wondering, Dr. Gilman, if we're going to learn what dark matter is, maybe through your research. Is that possible with this lensing thing?
So I guess it depends on what you mean by is. Like, so, we will certainly learn very general characteristics about what particle properties it must have. It's difficult with kind of cosmology because the types of experiments you do cast a very broad net, right? So you make a measurement, and that single measurement allows you to rule out an entire class of theories with many different possibilities for what the dark matter is. And then they are consistent with some other class of theories where there's still many different types of many different possibilities for the actual type of particle. And so I think it's possible that we will learn enough details about what dark matter, about the particle properties that it has, for us to have kind of a satisfactory imagination about what type of particle it is. But I think if you really want to get into like the nitty-gritty details of the particle interactions, you might have something coming from astrophysics that says it must have these kinds of generic properties on a particle physics level. And then you can maybe design an experiment on Earth in a particle collider, or maybe a direct detection experiment that could go out and detect that particle.
This program is this still on?
I turned it off because there's a little feedback.
Well, can you hear me?
Yeah.
Can you hear me?
The microphone's not connected to the Zoom, it's just connected to the audio.
Oh, all right.
He hears you, we hear you, you're good.
You won an award, I guess, Doctor, for this program. This was your dissertation we just watched, to get your PhD in physics?
The second half was what I worked on in my PhD. The first half, I've worked on it like a little bit, but I'm not, that's not really my primary area of expertise. But it has to do with lensing, so I guess I'm qualified to talk about it.
Well, I'm one of the few people in the club that don't have a PhD, so I don't know, but I think it's a book. You actually make something of a book you research, right? In which case, do you have the book? Can we buy it somewhere?
You mean the dissertation?
Yeah. Is it available as a book?
Yeah. Well, UCLA makes everything public, so you can Google like Daniel Gilman UCLA dissertation or something, and it should come up. And you can download it.
Do you teach a course up there in Toronto, or do you just do research?
No, for now, I'm just doing research. Yeah, postdocs are usually spared the additional burden of teaching, unless we volunteer. But yeah, no, for now, it's just research. Although I would like to teach. It's a nice way to give back, I think.
Sure.
Can I see there's a question here in the audience?
Okay,
Question, do we have enough resolution with the gravitational lensing to see new features with all the different instances that might be popping up, or is that, could you get a different perspective on the reflected, galaxy, the source of that, I guess?
So to repeat the question for people who couldn't hear that on Zoom, the question is, do each of those reflected versions of the galaxies that we're seeing that are gravitationally lensed, do we get different details in each of those images? Is that an accurate restate? Is there enough resolution to be able to see the differences of whatever that background galaxy is that we're looking at?
Yeah. So, right. So the lensed arcs, I think this is what you're referring to, like the lensed arc that's appearing behind me right now, like this thing, right? But for a galaxy lens. So they are spatially resolved. And it's resolved enough for you to get some kind of idea of what the source looks like. Now, whether you can resolve, like, I'm not sure off the top of my head, to what detail you can actually resolve the small scale structure of the source. If that was your question, I don't actually remember the answer off the top of my head. But I will say for dark matter stuff, I will just say for the dark matter stuff, the limiting factor in how well you can detect halos in lensed arcs is the image resolution that you have. So if you have much better imaging resolution, which people have with this very long baseline interferometer, so it's a radio telescope, it actually gives you spatial resolution of a few milliarc seconds. And this is actually potentially a game changer for this imaging technique, because now you can resolve even smaller deformations in the arc from low mass halos.
Did that answer your question?
Yeah.
well, Dr. Gilman, I know you may have discussed this and I missed it maybe. Why do we have 4 dots? Why aren't they all, here's a giant quasar galaxy with the same gravity in all directions. Behind it is another galaxy that we're seeing curved around it. Why doesn't it just always curve like an Einstein arc or smile, or what do they call that? The Einstein ring. Why would it pick 4 places and give us that galaxy? Do you know? Why is that?
So this is how I would think of it. So if you had a perfectly spherical deflector, something that was a perfect sphere, and it was perfectly aligned between you and a source, then that source would appear as a perfect Einstein ring. Okay.
Yeah.
This kind of symmetry is what you would expect. If you then took that perfect spherical deflector and you offset the source slightly, right, then you would have potentially 2 images of the source. You would have one where the light goes this way, and then one where the light goes the other way. Okay. So you can have a doubly imaged lens, or a double image lens, and they're actually much more common than quadruple image lenses. So they exist. Now it gives you 4 images is if now you break the spherical symmetry of the deflector. And so if you had a perfectly spherical deflector, then there's just 2 ways where the light can go. If you have something that is ellipsoidal or has a quadrupole moment, then it turns out that there are 4. And if you have an even more complicated mass distribution, like in a galaxy cluster, you can have something like the 5th image of the supernova, when then you have even more than 4 images, or there are more than 4 paths that connect you and the source. So the reason why we focus on lenses with 4 is because they're more informative than lenses with just 2 images, but they're not so complicated that they're like impossible to model, like some galaxy cluster with many, like 50 images or something like that. And I'm not saying it's impossible. A lot of people do this successfully. It's just not what we do for the dark matter science yet.
Any other questions? Yes, sir. Spell it out. That's your dad's friend, Rex Meach. Fake.
Rex.
At some point in the recent past, there was an attempt to explain some of these observations without positing the existence of dark matter at all, and using instead modified Newtonian gravity. Was that theory than took the asteroid.
So again, to restate, so you can hear it better on Zoom, there were some notions floating around ways to explain this without dark matter, instead using modified Newtonian physics. Did I restate that accurately? What's the status of that theory at this time?
So some people, propose that dark matter isn't real and we just don't understand gravity. And so the missing mass that we attribute to the presence of dark matter is actually just an artifact of us not understanding how gravity works. So this is the thing that Rex is referring to. Those types of theories, they do very well at explaining the things that they're like designed to explain. They have a hard time simultaneously explaining many different phenomena on different scales across the universe. And so I think for that reason, people are not very convinced of that possibility. So dark matter is still a better explanation for the variety of phenomena that we observe in the universe. I will say that if you manage to detect a completely dark population of 10 million solar mass concentrations at cosmological distance, I think this would be very difficult to explain with the theory of modified gravity. And if you did, it would be a little strange because this is not really a prediction of modified gravity. And so any kind of attempt to explain it with modified gravity would feel a little bit like you're transforming your theory in order to match new observations, whereas dark matter just kind of generically predicts that you should go out and find these halos, right? So I think in some ways you could view substructure lensing as a very robust test of theories of modified gravity, right? It's something else that they have to explain that dark matter does, kind of naturally explains.
There's a few of us in our club who managed to get a priceless, rare bumper sticker that somebody in the club came up with. I've got one proudly on my bumper. It says dark matters.
Yeah, that's good.
Mrs. McPartland, we got to get those and we'll sell them. They'll go like hotcakes, believe me, especially in the South. Unless there's another question, and I guess we got one more. Yell it out.
The question is there a difference between warm dark matter and hot dark matter?
Well, I mean, so there's like a spectrum of I guess you could think of it as temperature. What it really is a measure of the kind of average thermal motion of dark matter in the early universe. So on one extreme you have hot dark matter. So okay, I don't know if this is too technical, but if neutrinos were the dark matter, they would behave as hot dark matter. They're so light that they move relativistically, which means close to the speed of light for a long period of time. And then they would wipe out structure in the universe, basically. And then as you make it hotter, then you get into warm dark matter territory. And then as you make it colder, you then get into what we consider cold dark matter. But you can still, some cold dark matter is warmer than other varieties of cold dark matter, right? It's just that given the experiments we can do today, anything colder than a certain threshold, we just call cold dark matter. But there's a spectrum of possibilities.
But the fact that light, which is a wave and a particle, is a very unique particle because it doesn't have any weight. All it has is energy, right? And yet it goes 0 to 186,000 miles in a second and can stop in an atom on a dime. And yet it can be sucked into black holes and go around galaxies and give us lensing. Black or dark matter, we can't see, but it does have some mass, right? Even though it doesn't interact, you suppose black holes can suck in dark matter?
Yes.
You think? We think so? All that black dark matter inside there, the singularity along with the regular atoms and matter together.
Yeah, I mean, if dark matter appears to follow general relativity, and so if it gets sucked into a black hole, it's never coming out, just like regular matter.
But I'm thinking, Doctor, that even the Earth probably gravitationally lenses just like pulling an incoming asteroid a little off its, trajectory, just that there's so little amount of light waves, we wouldn't be able to see it, would we? They did see some on the sun. I believe that's what proved that there was lensing. I think Einstein proposed it, and we didn't know until there was a total eclipse of the sun, and they actually saw a star that was behind the sun come around it. Is that true, or did I make that up?
No, that's, yes. So one of the confirmations of general relativity was a measurement of gravitational lensing by the sun, just like you described it, of a star. Yeah, and so I mean, to that point, right, I think something that I heard a few years ago that I kind of like is that everything you see is lensed, right? Nothing that you observe is actually the intrinsic way that thing looks, because the light that reaches you is always being deflected by anything with mass. Of course, in practical circumstances, this doesn't really matter. It only matters if the lens is a galaxy, right? And it's
One of our members has a question. This man used to lecture to us.
I am puzzled by the idea of cold or of dark matter that is other than cold. Because I thought that the definition of dark matter was something that it existed, it had a gravitational effect, but did not radiate at all. Otherwise, what would dark mean?
Doesn't interfere with regular matter. We don't have anything to do with each other. Did you hear the question?
Yeah, so I think this is kind of an unfortunate consequence of the name. So again, the hot doesn't actually, it's referring to the motion of the velocity of the particles at early times. And so, if something is hot, it's because the average thermal motion of the particles is high, right? They're moving at some large speed. And that's actually what's meant by temperature. So when people talk about hot dark matter, what they're talking about is a dark matter particle that at early times is moving very quickly. Doesn't actually have to do with light or interaction with the standard model per se.
Wow. Any other questions? One more. Yes, sir.
Why does it take a whole year for the fifth image to appear, and why does it appear so far away from that image?
So the question is, why did it take another extra year for that fifth image to appear? And what was the second part?
And why does it appear so far away?
And why does it appear so far away from the other four images?
Right, yeah. So it was a little hard to tell on the slide, but there was actually a cluster of galaxies that was doing the lensing there. So there was this elliptical galaxy that was producing the four images that you saw. But then kind of around off screen, there were other galaxies. And so this lens system was actually very complicated. And it's complicated enough that there was a fifth image, not just four. And it turned out that the path that connected us to the source in the fifth way just so happened to appear, kind of far away from the other four paths. And this is just determined by the configuration of the mass in the lens. As for why it appeared when it did, this was luck. I mean, it could have, it could have appeared, in 1,000 years, right? And in some sense, it was just lucky that it showed up. It did. And yeah, I encourage you to look at the paper. The lead author of those papers was Pat Kelly. He's at the University of Minnesota, I believe, and those papers and some of the ones that preceded it were pretty amazing. I suggest you go read them. Or the
Dr. Dan Gilman, if you ever come to Santa Barbara, do visit us. I would like to quickly make one statement and then turn it over to the president. Next month, on Friday, May 5th, we'll have a local speaker from LCO, which stands for Las Cumbres Observatories. It's one of their upcoming, I think it's a pre-doctoral student on his way. His name is Joseph Farah. And the director, Sandy Searle, you've met her, I haven't, I've been talking to her online. She sent me an email today talking about a full eclipse of the sun we're going to have a year from tomorrow, on Monday, the 8th of April, 2024, which will go across northern Mexico, Texas, and eastern Canada. If you're still there in Toronto, you may be able to see the full sun eclipse. The rest of us will get a partial. You might even get it in Chicago if you're there by then. But
That's
I thank
amazing.
you very much, and we're going to give you a couple of things. Can we send you some money for talking to us, and so you can afford the Canadian gas, $100 honorarium, sir? We had your address. I'd love to send it to you.
Of course.
Along with our priceless Chumash porcelain cup that was dug up in the back. They're worth thousands of dollars.
Oh, great.
Sell
Yeah,
them for 10. Well, you're going to trip over this.
I'm
You
not
better go
gonna
around.
come any farther.
And if you haven't got enough dark matter, quick plug just premiered Ends of the Universe, Dark Matter in the Planetarium last weekend. So come back Saturday or Sunday at 3 p.m.
And Monday morning.
Is this on? No.
No.
It's through there. Okay.
What's that? Yeah, every Saturday and Sunday at 3 o'clock for the next 3 months.
Then on Monday morning, 11 o'clock, tune us in on YouTube, Santa Barbara Astronomical, or SBAU Astro Hour. Mr. President Jerry Wilson.
Thank you,
Let's have a
Dr.
hand for our
Gilman.
president. And for Dan Gilman, thank you.
Thank you.
Excellent and fascinating talk. Thank you very much.
Oh, thank you guys for having me. It was great.
Okay, and I think that concludes our meeting for tonight. We'll see you all maybe a month from now.
Thank you.
Yeah.
All right. Everyone wave goodbye. I'll end the Zoom now. Thanks, everyone.
Bye.
Thanks again, Dr. Gilman. Great talk.
Oh, thanks.